So we have a standard normal random variable with mean 0 standard deviation 1. And if we square that, we have chi-squared with 1 degrees of freedom. If we have nu of them and we add them up, given that they are independent, we get a chi-squared distribution with nu degrees of freedom. And if we have, again, basically a ratio of a standard normal distribution and basically a chi-square distribution, which is divided by its degrees of freedom, and basically the square root of a chi-square distribution, then we have t distribution with nu degrees of freedom. And finally, if we have two chi-square distribution, one with basically d1 degrees of freedom, the other one with d2 degrees of freedom, and if we sort of scale them by dividing them actually with degrees of freedom, then the ratio of a scaled chi-square distribution has F distribution with D1 and D2 degrees of freedom. Okay? Then we said why these are important, because we are going to use them for finding sampling distributions. Sampling distributions means if you have a population with some distribution, in that case we usually assume that it's coming from a normal distribution. We don't know the parameters mu and sigma squared, and what we do, we collect a random sample, and then we can define some functions on those random samples, like x bar, s squared. And the distribution of this x bar is called sampling distribution. Distribution of s squared is sampling distribution. And we want to see what are those distributions. Okay? By the way, the definition of random sample is what? Do you remember? Random sample means they should be independent and identical. So IID, independently identically distributed. Okay? Then we said central limit theorem. Let's just start with the case that we don't know the underlying distribution. It could be any distribution. Okay? Then we collect a sample and we calculate x bar. We want to see what would be the distribution of x bar. Actually, we don't know, but if n is large enough, then we can say x bar approximately follows a normal distribution with the same mean, but the variance divided by n. So a smaller variance. This is very important because in reality we may not know the distribution of the population, but we can still do some inferences on x bar. Okay, using x bar, because we know the distribution of x bar is normal. Approximately normal. Okay? Any question? Good here. Okay. So actually I showed you a simulation to see how it works. There is one example here. Let's say we have an electronic company which manufactures resistors. And mean resistance of 100 ohms. So the sample size is 100, and the mean resistance is of 100 ohm, and basically it follows a normal distribution, I'm sorry, a non-normal distribution, but we know the standard deviation, we don't know mean. Sigma is, sorry, I think I made a mistake. It says mu is 100 and sigma is 10. So we have resistance as our random variable, non-normal distributed. I put it something, but we know that mu is equal to 100 and sigma is equal to 10, which is this guys here. It says, let's say we have a random sample and we want to see what would be the probability of the average of this random sample is less than 95. What is this probability? Okay? And the sample size in this case is 25. So based on central limit theorem, I can say X bar follows a normal distribution or approximately normal distribution because N25 is a good number. Okay. Usually they say if the distribution is skewed, then 30 is fine. Otherwise, around 20 should be okay. Okay. If the distribution is kind of like more symmetric, you need less number of sample size. I showed you, for example, in uniform distribution, we only need like 5. So this is for CLT to hold. So usually n greater than 30 is basically is considered as large. In this case, 25 is okay. So X bar follows a normal distribution with mu equal to 100 and the variance equal to 100 divided by 25. Okay, because sigma is 10. So what I need to do, I need to standardize it. Okay. And in this case is 95 minus 100 divided by 125. Let me put it mu of X bar just to distinguish between these two. So this is mean of X bar, this is variance of X bar, this is mu of X, and this is the standard deviation of X. Sigma, which is 10, divided by square root of 25. So what is this guy? Z. So probability of Z less than minus 0.25. Which in this case is 0.0062. Okay? That's one simple example how we can use central limit theorem. Again, we don't know the distribution of X, but X bar, based on central limit theorem, just write it down here, CLT, approximately follows a normal distribution with this mean and this variance. Okay? Any questions? Is it clear? Okay. So how about other distribution? What if we know, so for central limit theorem, we assume that we don't know the underlying distribution. Okay? So what if we know that? What if the underlying distribution is normal? Okay? Then can you tell me something about X bar or something about distribution of SS squared? Okay? Let's see. We use basically those distributions that you learned before, normal, chi-square distribution, T distribution, F distribution, to say something about X bar and distribution of X bar and SS squared. Okay? And so the question is, when should you use each distribution? And the other one is how to use each distribution, under what scenarios. Main assumption again, samples are collected from a population following normal distribution. This is not CLT. CLT doesn't have this assumption. Okay. Let's just start with a very simple case. Are you done with that? Very simple case. Yeah, go ahead.
Besides the, if we know that it's a normal distribution and using the normal distribution to learn things about it, like mu and all that, is this kind of, if you have more than one variable or...
What do you mean by more than one variable? You mean
maybe you have two chi-squared distributions that are both normal and you want to examine them together, because if you already know it's normal, why not just use the normal?
Exactly. So you will see for more than one population, when you have two, what would be the difference of the mean? What would be the ratio of the variances? And these are all related to chi-square, F, T, whatever distributions that we learned before. Yeah, exactly. So let's say now we have a different setting. a normal population with this mean and variance, and we want to know what would be the distribution for x bar. And as you can see, the distribution of x bar again follows a normal distribution, exactly, not approximately. I want you to see the difference between this guy and central limit theorem. Central limit theorem says approximately. This one is exactly for any n, for any sample size. Okay? So it doesn't matter for large sample size, for a small sample size is correct. For n equal to 2, this statement is correct. Okay? So when you have normal distribution, x bar follows a normal distribution with this mean and variance. This part is very similar to central limit theorem, but the differences are here. Exactly, not approximately. It doesn't require large n. For any n, that's correct. Okay? Any questions? Is it clear? So it makes basically our job easier. So since it follows a normal distribution, this guy follows a standard normal distribution. How about two populations? So what if I have one population, mu1 and sigma squared 1, the other population, again normal, with mu2 and sigma squared 2. I collect the sample, this one, let's say y1 up to yn. Okay? And I want to see, so I know that y bar follows a normal distribution with mu2 and sigma 2 squared. Okay? So I have two populations. I have two random samples. And these random samples are independent of each other. Okay? I know each of sample averages, each of them follows a normal distribution. This one mu1 and sigma 1 squared divided by n. This one mu2 and sigma 2 squared divided by n. Let's call this one n1, this call n2. Two different sample sizes. Okay? Now question is, what is the distribution of x bar minus y bar? Okay? We say follows a normal distribution with a difference of the mean but summation of variances. Okay? Do you remember why? Why this is correct? Nobody can tell me? You've seen this before. There was a fact. Yes, exactly. So first of all, any linear combination of independent normal random variable is normal. So that's why this is linear combination. This is normal. Okay? So expected value of the linear combination is the what? Linear combination of the expected values. Remember? So expected value of this guy is expected value of x bar minus expected value of y bar. How about the variance? So if they are independent, which is our main assumption, so these guys and these guys are independent, then it would be variance of the linear combination is the linear combination of the variances with coefficient squared. You remember that? So that's the coefficient squared variance of x bar. The coefficient of this guy is minus 1 squared variance of y bar, which gives you sigma 1 squared divided by n1, sigma 2 squared divided by n2. That's exactly what you have. Okay? Any questions? Is it clear? Okay. And then you can standardize it easily. And standardize it by subtracting mu and dividing by standard deviation. So here is one example. we have two mating parts are assembled, as you can see. One is like a piston and the other one is cylinder. And so X is inner diameter of the cylinder and Y is the outer diameter of pistons. Okay? Both of them follow a normal distribution, one with this mean and variance and the other one with this mean and variance. Okay? Let's say we have a random sample. And we want to see what would be the probability of X bar minus Y bar greater than 0. Okay? I'll give you a couple of minutes to work on that. Okay, we are just directly using this equation. Relationship. X bar minus Y bar follows a normal distribution with this mu and this variance. So standardize it based on this mu and variance. This would be this number. Do you have any numbers for that? The calculator? Anybody? This one? Altogether, to the square root? So this is standard normal distribution. So it's probability of Z. What is this number? 0.0224. So it's this guy divided by 0.0224. Then we can find easily this probability from the table. Okay? Standard normal table. Yeah. Yeah, actually, this should be sigma centimeter cube. I'm sorry, a square. This one also. So, yeah, thank you. So these are a square. This guy and this guy. Because those are variances. Any question? Yep.
Why is and the 5 and 10? Where does that come from?
5 and 10. Oh, it's the sample size. Yeah, that's the conclusion. So we have it here.
Oh, okay.
So we have n1 equal to 5 and n2 equal to 10. And that's basically based on this. Okay? So sigma 1 squared divided by n1, sigma 2 squared divided by n2, and it's right here. Okay? Any other questions? Okay, good. So let's see. So what is the distribution of variance? If I have a normal distribution for the population, what would be the distribution for S squared? Okay? And that's easy because I can easily show that n minus 1 S squared divided by sigma squared follows a chi-square distribution with n minus 1 degrees of freedom. Okay? And do you know why? Okay, let me see.
If
What?
if S squared, since you know it's normal, you can
No,
pretty
actually,
much
S squared is not normal. So that's the point. So these are constant. So I want to know what S squared distribution is. I would say, okay, S squared probably I don't know. But if I multiply those constant, then it's going to be chi-square distribution with n minus 1 degrees of freedom. And here is the proof why it is chi-square distribution. So let me start with the definition of S squared. What is it? Summation of xi minus x bar squared divided by n minus 1. Okay? So n minus 1 S squared sigma squared is, if I just plug in this, the definition in here, then I get simply this guy. You agree? So n minus 1 is cancel out with this n minus 1. So I have this guy divided by sigma squared. Okay? Any questions? So let me write. So we have it here. So I want to know what is the distribution of this guy. Okay. So this is very simple and important fact that I can write basically the deviation from mean, a square deviation from mean, as these two terms, summation of these two terms. Okay? And it's easy to show. You just need to basically expand each term, and you will see there are some terms that cancel out each other, and then you get this one. So the left side and right side is going to be the same. I'm going to use this fact. Okay? So this is important. And you will see why I'm going to use it. Because I have this guy, which is right here. Okay? And I have this guy, which is, I know how to use it. You will see in a minute. The first step is to divide it by what? Sigma squared. Because I'm looking for this quantity. I want to know what is the distribution of this quantity. So I divide both sides by sigma squared. It gives me this guy for the first part. How about the second part? Xi minus x bar squared divided by, let me just write it down smaller, sigma squared plus, so there is no I index here. So what is this guy? Is n times this quantity. You agree? This is n mu x bar squared. Because there is no I index. It's constant with respect to I. Okay, so then I have okay. So let me do a little bit of trick on this. So let's see. I have this guy here. I have this guy here. And I have write it down as x bar minus mu. And then this way. Okay? So this guy and this guy are the same thing. I just rearrange it. Okay, I just rearrange. I put n here in the basically denominator, and I put everything inside the squared function. Does it make sense? Any questions so far? Are we good? Okay. Now you tell me. If you don't have question, I'll ask a question. So what is the distribution of this guy inside the parentheses? What is it? Inside. Xi minus mu divided by sigma. B for a squared. It's a standard normal. After a squared is what? Chi-squared. How many of them I have? N. Okay? So what would be the distribution of this guy? Chi-squared with n degrees of freedom. Again, this is a standard normal. A squared, chi-squared with 1 degrees of freedom. I'm adding the up n of them. So it's chi-squared with n degrees of freedom. Does it make sense? So this guy, I don't know. I want to basically find the distribution. What is the distribution of this guy? X bar follows a normal distribution. I don't have it anymore. But X bar follows a normal distribution. Let me write it down here. With this mu and this variance. Remember? So this is a standardization of that. So it's z distribution. The squared is chi-squared. How many degrees of freedom? What? How many? N? 1, 2?
1.
You only have one of them. So it's chi-squared with 1 degrees of freedom. So chi-squared with n degrees of freedom. Chi-squared with 1 degrees of freedom. What is this guy? Chi-squared with n minus 1 degrees of freedom. Because you remember, summation of 2 chi-squared is going to be a chi-squared with n minus 1 degree, with the summation of the degrees of freedom. So if it is n, if it is 1, this should be n minus 1. And that's why this guy follows the chi-square distribution with n minus 1. Very simple proof. Any questions? Yeah.
Based on the definitions that we've set out with, is there any way we can just look at maybe s squared over
Not for this one, actually.
over
No.
n minus 1?
No. So we use the definition exactly here. So that's basically where we use. Yeah. That's where we basically use the definition. Here and here. Actually, we are using two things here. One is the fact that x bar follows a normal distribution. And the second one is the z squared is going to be a chi-squared. So two things are using here. Any questions? We good? So let's see. Suppose the patient waiting time in an emergency room is normally distributed. Okay? And we know the value of sigma is 0.5. So x is normally distributed. I don't know mu, but sigma is 0.5. We have a random sample of size 3. So 3 patients. And we want to find the probability. So this gives us S squared, which is sample variance, okay, or sample, let's say S, which is sample standard deviation. So it says calculate the probability that the sample standard deviation, which is S, is greater than 0.5. Okay? I'll give you a couple of minutes to work on that. That's interesting. Very nice example. You may or may not need this fact, actually. Anybody got any number? Probably e to the power of something. Okay, let's see. So I need to find the distribution of S. I don't know, but I know the distribution of S squared. Okay? So what I'm going to do, I said this is the same as calculating probability of S squared greater than 0.25. Then what should I do? I should change it to this quantity by multiplying n minus 1 and dividing sigma squared. In this case, multiplying 2, which is n minus 1. Probability of n minus 1 S squared, sigma squared. So n minus 1 is 3 minus 1 times S squared, which, I'm sorry, 0.25 multiplying both sides and dividing by sigma squared, which is 0.25 in this case. Is it clear? So again, the first step is to find distribution of S. I don't know, so I try to change this quantity to a quantity that I know the distribution for, which is n minus 1 S squared divided by sigma squared. So a squared, both sides gives you this. Multiply n minus 1 and divide by sigma squared. Multiply by n minus 1, divide by sigma squared. Your sigma is 0.5. Therefore, your sigma squared is 0.25. So basically, I know the distribution of this guy, which is chi squared with n minus 1 degrees of freedom. Okay, 2 degrees of freedom. Greater than number, which is 2. So I want to find probability of a chi-square distribution with 2 degrees of freedom greater than 2. And this is the fact that we learned basically last week. Chi-square distribution in general is not easy to integrate. So what we do, but for when degrees of freedom is equal to 2, it reduces to exponential distribution. Therefore, I can integrate an exponential distribution. Let me just continue here. So chi-square distribution with 2 degrees of freedom is the same as exponential distribution with lambda equal to 0.5. Therefore, this quantity, probability of chi-square distribution with 2 degrees of freedom greater than 2, can be obtained by integrating from 2 to infinity this PDF function. Which is that guy. Any questions? Go ahead.
Greater than 2, why 2?
Oh, just simplifying this. Yeah, that's it. Yeah, we simplify that, then we have to. Questions? Is it clear? So that's the way we need to do that. Actually, when you have a quantity which is not familiar, we need to basically play with that quantity and make it and transform it to something that we know. Okay. Is it clear? Good. So what if we have a distribution? Actually, the underlying distribution is normal. The case that underlying distribution is normal. With this mu, but the variance is unknown. So we don't know variance. Okay? And again, we have a random sample. We want to see what would be the distribution of x bar. Usually when we don't know variance, we estimate it using what? S squared. Okay? So we can say, how about doing this? We know that x bar minus mu divided by this guy follows a standard normal distribution. Remember that? But in this case, I don't know sigma. So I estimated with, let's say, S. If I just replace sigma with S, then this distribution changes from normal to T distribution with n minus 1 degrees of freedom. Okay? That's what we have. So distribution of x bar is not normal anymore, is T, when you don't know the variance. Okay? So standardized x bar follows a T distribution with n minus 1 degrees of freedom. Anybody knows why? just erase that board and show you why. Do you remember the definition of t distribution? It was what? It is z divided by a chi-square distribution divided by degrees of freedom. Okay, so chi-square distribution with new degrees of freedom divided by degrees of freedom, and then we calculate the square root of that. So this is t distribution with what? New degrees of freedom. You remember that? So let me use this guy and try to make it this guy. So x bar follows a normal distribution in general if variance is known with this variance. You agree? Okay? So I standardize it. This is our z that we are looking for. That's the z we are looking for. How about the chi-square? I need to have a chi-square as well. You just saw one chi-square in the previous slide. What was that? This guy. You remember? So n minus 1 s squared divided by sigma squared is a chi-square distribution with n minus 1 degrees of freedom. So what I'm going to do, because I need to basically divide it by degrees of freedom and then find the square root. Okay? So n minus 1 s squared sigma squared divide by degrees of freedom, and then a square root. Okay? That's the quantity for denominator I'm looking for. Is it clear? Now what is the next step? Just find the ratio. Okay? So x bar minus mu sigma 1, and so I can just simply get rid of this guy. They cancel out each other. S squared sigma squared. So what is this distribution? According to the definition, is t. What is the degrees of freedom? Degrees of freedom is coming from the chi-square distribution. The chi-square degrees of freedom is n minus 1. So it should be t with n minus 1 degrees of freedom. You agree? And so let's do some simplification here. We can just get rid of sigma. Okay? They cancel out each other. Or maybe I can continue here. This gives me x bar minus mu s, which is t with n minus 1 degrees of freedom, what I have here. Okay? If you simplify this guy, then you get exactly what you're looking for.
Term for the population standard deviation over your sample deviation? Is that kind of like a
Sigma. So sigma is population standard deviation. S is sample standard deviation. Sigma squared is population variance. S squared is sample variance. So that's the terminology that we use.
of the equations? We had to multiply by a factor of sigma over s. Does that have any?
Oh no. This is right here. I'm not multiplying. So this one, if you the square root of this guy is s over sigma. This is basically in denominator, so I can make it multiplication and reverse it.
Talking about
Okay.
when you were describing kind of getting to a t, does that have any value, knowing kind of the ratio of your population standard deviation to your sample deviation?
That's a good point. We have another distribution which is based on, you will see the next distribution, which is based on the ratio of sample standard deviation and population standard deviation. Or, I'm sorry, sample variance and the population variance. So that ratio, we use it for another distribution. But does it have any name? No. Not that I know of. Any other questions? Is it clear? Do you want me to repeat some part of it? Go over again? You go ahead.
Can you go over why the denominator we use the chi-square distribution? Is it just because it works out?
Oh, yes, exactly. Because that's the definition. So in order to have t, we need to have z numerator and a chi-square distribution in denominator. So what I'm trying to do, I'm recreating this definition. Okay? Then I get a z distribution numerator and a chi distribution in denominator. And basically, it's just simply replacing z with this guy and this by this quantity. Does it make sense? Sure. Any other questions? Good? Yeah, go ahead.
Where did the extra n minus 1 in the, when you simplify the chi-squared, is that just from the description of the...
Oh, yes. So you can see is the chi-squared divided by degrees of freedom. Okay? So this is degrees of freedom. And this itself is a chi-square. Okay? Any other question? These are good, actually. You good? Okay. So one example, I think that would be the last example. So we have the diameter of a manufactured PVC pipe follows a normal distribution with mean 1 and variance sigma squared that we don't know. So let's say mu is 1. And sigma squared we don't know. And find limit u such that the probability that the mean diameter of a random sample of n equal to none is greater than u is 0.05. So basically, the average of a random sample greater than u, this probability, we want this probability to be 0.05. And we know that n is equal to, let's say, 9. Okay? However, based on a random sample of size 9, we know that the standard deviation, sample standard deviation is 0.1. So we have this information. Okay? So first of all, if I knew sigma, okay, then what distribution should I use for x bar for solving this probability? What? I would use
Normal.
standard normal. Standardize it and normal distribution. We don't know sigma, but we have S, which can replace sigma. Then we need to use what? T distribution. So we know that probability, we have it right here actually. Probability of x bar minus mu divided by S divided by square root of n. Mu is 1. And S is 0.1, and N is 9. This is 0.05. Okay? So let's call this guy, this is T distribution. With how many degrees of freedom? N minus 1 or 9 minus 1 in this case. What is this guy? Anybody can tell me? It's called, there is a name for that actually. So you can say it's a function. You've seen this before. T of something and something. T of 0.05 and 8 degrees of freedom. Look at this. You remember the definition of T of alpha and nu? Is the point that probability after this point, after means greater than. Probability after this point is alpha. Okay? So you have a point that probability of T distribution after this point is 0.05. So what is this point? T of 0.05. That's the definition of T of alpha. Does it make sense? Okay? So you have a point that probability after this point is 0.05. So this is T 0.05 and 8 degrees of freedom. Are we good? So we can use table for that. So 0.05 is right here. 8 degrees of freedom is right here. So we get 1.86. So U minus 1.1 divided by 9, this guy is 1.86, is that correct? Then I can solve it easily for U, which is 3, U would be 0.6 divided by 3 plus 1. Is that right? Yeah. That's U. Is it clear? So, first of all, we change it to T. T distribution with 8 degrees of freedom greater than 1 point is 0.05, that probability. So that's the definition of T 0.05 and 8 degrees of freedom. We use table, we get that number, and from that we solve it for U. Any questions? See you on Wednesday.